Good data science users in the audience, data scientists, data engineers, mostly familiar faces as well, and some new faces. Who's first time in this meetup? It's awesome. A lot of brand new users. That's always good. This is the first time you're doing it kind of in Kabbali. It's a very good community feel for it, right? It gets you that really grassroots effect that we are trying to really make happen, and it also happens to be the nearest venue for our office and lots of people in Silicon Valley. It's easy to reach, right? So we'll try and keep the same venue if it works for us over the course of the next few months. Tonight, there are lots of interesting changes you've seen, mostly because we've had a phenomenal community person who's joined us, Community Candel. Obviously, in the audience is some of the members from H2O, Steve Clifter. Go to him about H2O dev problems. Some new people who's less than first day, Joel. So you'll hear from Joel as he keeps the drum beat going. But it's not just about H2O, it's about the community. So one of the quotes that we really live and die by is that code is incomplete without the community. And actually, most things are incomplete. There's no community around it. And we've been trying to build this over the course of many, probably 90th meetup, right, in the last year and a quarter. So we've been doing it from March 2013. So it's about a year plus quarter, one or two every week, right, which is pretty good for a startup that's our size. But we want to now encourage users of H2O to start speaking. So we're beginning to build momentum towards H2O Summit, which is towards the end of the year. So we want users to participate. Communities die if they don't have participation, right? You can only look for so long. You want to jump in and get your hands wet with H2O. And there's lots of people in the audience who will probably get you started. If there's ways we can help build the community even more participatively, please give us suggestions, add to the meetup's feedback on what else you'd like to see. So with that, I want to bring focus to tonight's talk, deep learning with H2O, but with examples. So some of you have seen deep learning talks before, and over the last few weeks and over the month or so, we've had a chance to actually have a couple of interns work with Arno, as well as other users work with Arno from open source and the team. And I think we learned a heck of a lot on how to make better models with deep learning. So I think it's about time to now talk about hands-on examples at the KDD. How many of you have been at the KDD? Amy was there. At the KDD, there was a full day of training session on deep learning. And our vision is that most of the training will be compacted over the course of the next many meetups. And hopefully we'll do a very good hands-on session so you can actually get really your hands dirty with real data. With that, tonight we have Arno. A lot of you are new, so Arno is reasonably new to Xdata. January, December, right? 9 months. 9 months into it. So they say it takes 9 months to do anything right? So it's organic cycles to life. And 9 months to build a product, 9 months to market it, and then the way it really sustains. So it's 9 months since he's been working on deep learning. So it's something great to offer, and I think we have a bio slide in there. So I'll just leave it that he's a physicist hacker, right? And he was the one person I told someone recently that he's one guy where I knew I was losing a customer in another meeting, but I sent Cliff to take care of it and stayed with him, and I'm not going to regret it. So with that, welcome and have a great evening.
Thank you, Sri. Thank you, Candel. So we're going to start. This is the starting point for our audio synchronization. All right. So I've been at Slack for 6 years after I got my PhD in physics in Switzerland, and that's when I learned to use supercomputers. We had access to 1 million CPU hours per person per year or something like that. So that was tens of thousands of nodes, distributed big systems, the #1 supercomputer in the world basically, and you could run anything on it. That of course fitted the Department of Energy guidelines for what we had to research on, but it was particle accelerators and stuff like that. So that was fun. Then I spent 3 years at Skytree doing machine learning. I was one of the earliest engineers there, founding engineer team. And now I'm at Hexadata, and I'm doing more machine learning. I'm getting better and better at it, and I'm doing exciting stuff here with H2O, and we'll show you much more about that. And also, I recently got named Big Data All-Star, whatever, shameless plug, yes, thanks. Fortune magazine. So yeah, the talk today will be mostly hands-on for me. You will just watch, but you can do the same thing at home. This is all reproducible. There's no tricks or anything. That's all open source. The data is open. The parameters are open. The scripts are open. So you're encouraged to do this yourself and then compete at Kaggle competitions, for example. We're going to talk about certain different data sets, but before we go too much into details, I'll have to explain to you what deep learning is. Who knows what deep learning is? Have? By the way, who's using machine learning tools on a daily basis already? So data scientists, yes. Who's using R? Oh wow, a lot of people using R. Who's using Python? Hadoop? Like everybody, right? Everybody uses a little bit of everything these days. So yes, great. So H2O, she introduced the company earlier a little bit. It's still small. It's about 20 people right now. We're growing fast, a little more than 20 people, I would guess, from this picture there. 14,000 commits in one repository on GitHub. That's a lot of commits. 35 contributors. This is the #1 Java machine learning tool on GitHub. If you search for GitHub and then machine learning and Java, this will be the #1. So we're glad to be up there. We have great advisors. You see Stephen Boyd, Rob Tibshirani, Trevor Hasty. They wrote the books on machine learning. You'll also see that Clive, for example, up there, actually knows what he's doing about Java, right? He wrote the Java compiler or the hotspot or parts of it. He made Java fast. He actually made Java fast. That's a big statement, because back in the days, everybody said, no, it has to be Fortran or C. Forget Java, it's too slow. We know how to use Java well. That's why we can make it work.
Round of applause. I'll tell you what, we tried to make Scala fast, and he's going to pick that up next, right?
Yes, Scala is next. So customers want speed, right? They want in-memory, they want interactive analytics. They don't want to wait overnight every time. They want it to be on big data. They have petabytes of data, terabytes of data, even hundreds of gigabytes. Sounds not that big, but it's actually quite big for real machine learning tasks, other than just counting stuff. So big data means distributed. You have to run on a cloud. Ideally, a supercomputing server farm, not just a Amazon cloud, or maybe a good Amazon cloud. So you have to balance money versus time and so on. But either way, it has to be distributed. It has to be open source so you know what you're getting. You don't want to have a black box that just does something. And also you want to be able to extend it, right? So you want APIs, you want development kits, and so on. So this is all baked into H2O by design. So H2O can be without Hadoop or on top of Hadoop. For us, Hadoop is mostly an HDFS server, and maybe a way to launch it through Yarn, for example. But it just plays a dummy mapper and just does its job, which means it computes using memory and CPUs, and it's just going to be hungry using whatever resources it can get. It can run on top of Yarn, as said, and it can also be just standalone on your laptop without any Hadoop, right? Just java-jar, h2o.jar, enter, you'll have a running instance of H2O. And you'll see that on my laptop later. It connects to R via JSON, so you can remote control it from R. That's one of the big strengths. You can also connect through Python or Scala. They're all going to add these capabilities more and more as we go along. Scala and Python are working, R is working, JSON is the REST API, everything's in there. and we can do exciting stuff with it. For example, you can do machine learning algorithms, right? Deep learning is just one of them, but you can also just ask from R to say, like, here's a terabyte, I want to do some munging on the data, I want to compute sine of a column or something, or cosine, or multiply by 7, or compute the norm, or the mean, or the summary, quantiles, all this kind of stuff. That's more than just machine learning algorithms. It's a real big data math platform. There's a prediction engine built in that you can use to do the deployment of your model in real time, like Storm, for example, real time scenarios where you just want to score incoming points. Is this fraud or not? And that can be done with this nano-fast scoring engine, which is actually Java code that just is if else, this number greater than this number. There's no heap allocation. It's just as fast as it can be processed by a processor without any main memory access, just level 1 cache. And that's really fast. That is the fastest scoring engine you'll find. That's built in the product. It can spit out this Java code as you build your model. And how does it all work inside? Well, it's based on a distributed key value store here. That's the secret thing inside of H2O. It's a distributed non-blocking hash map where you can put in a value, and everybody knows that it's there, and everybody has the consistent view of that thing that's in the database, so to speak. And that thing is just bits. Anything you want to store, you can put it under a key. The key is a long identifier, and you say, hey, what's under that key? You get a consistent view, consistent with the Java memory model. Someone else updates it, then you get, next time when you ask, you get the new value. You always get a correct value at the time. So that's pretty important as a building block. And you can do MapReduce on top of that, and we have a fine-grained MapReduce paradigm where we, instead of copying all the results to the hard drives of the HDFS system and then doing a shuffle that's global and all that, we're doing reduces from between each mapper and the other mapper that just finished. And these little mappers are all threads, single-threaded little things that run, and as soon as they're done, they reduce. So you have immediate reductions happening all over the place, fine-grained MapReduce, and in the end you have no shuffle phase, no hard drive dumping phase, it's all in memory, it's all fast, and you get really fast speeds in that MapReduce paradigm. So this is basically what we use to make these machine learning algorithms work fast. And the data can be sucked in from HDFS, as I mentioned, or S3, or a flat file on your, or Excel, whatever you like. Basically any data that you have that's structured in the table format can be sucked in. Categorical, numbers, strings, whatever it is, dates.
Excuse me?
Yes?
So can you tell me? Oh, okay, so go ahead. I was trying to ask you this part.
Okay, great. So yes, you can go to this link here. This slides will be available. You can click on these links, they're all live, and they will point you to whatever they're pointing here, so you don't have to write down anything. Databricks wrote a blog about us, or published a blog that said that the two of us are going to combine efforts to make machine learning on top of Spark better, and that's exactly what we're doing these days. So the goal is to have the nice platform of Spark where you can do SQL and data munging Hadoop style, but faster, with all kinds of knobs and bells and whistles, and then you can do the fast machine learning that H2O has developed in the last few years on top of that. And that's going to be a really, really strong combination. Here's a quick preview. In 2 weeks from now, on Thursday, there will be a meetup about just that, sparkling water, spark and water. This is running code. Cliff was working on that together with Michal last few days, right? This is something in the sort of make H2O run on top of an RDD that comes out of Spark. And that's just demo code. It's basically a sneak preview for your eyes only. This is going to be exciting. R has CRAN as a repository, and we are inside of CRAN. So if you just type import me this module, it'll just work, and you'll have H2O on your R. What does it mean? Well, normally it just launches a H2O work farm on your laptop, a single node, multi-core little worker farm. But you can, of course, run your cloud on a Hadoop cluster with 50 nodes, and then connect your R session to that guy, and say, hey, I want to download a terabyte from HDFS and run logistic regression on it, and then do a summary on the data, and then do k-means, and then do deep learning, and so on. And in the end, you get back maybe the AUC number into a table inside of R. And that's the only number you copy back to your laptop. Everything else stays on the supercomputer or your cluster. So that's the strength. And John Chambers was recently giving a presentation, and he mentioned us as one of the 3 promising projects for the future of R. It's certainly a great tool to use R on big data. And this is how it would look like in RStudio. Who's using RStudio these days? Okay, great. So you just say install package and so on, and then library, and then that's it, right? And then you have h2o dot something instead of dot something. So let's say instead of saying I want to run k-means, you say h2o dot k-means. It's that simple. And the parameters are very similar. There's help, there's documentation. We have an R vignette documentation for deep learning and GBM at the point. But we'll add more vignettes. We have example codes. If you don't know where to find this stuff, ask us, support@oxdata.com. There's a lot of things you can do with R, as you know, and with H2O. Together, it's really powerful. All right, let's go to physics, since I studied that. No, just kidding. I actually worked on this project, but not this one, the next one. You know what LHC is, right? The big collider that I found the Higgs particle. There's the next project, which is called CLIC, which is the compact linear collider. That's what I worked on 5 years ago on that supercomputer. So this is all long-term stuff. This was $13 billion to find the Higgs particle, 16 miles long circumference, tunnel in Switzerland and France, 120 megawatts, minus 456 degrees Fahrenheit. It's all super extreme, right? What are they doing? Nothing else but colliding protons, and they're trying to see whether what comes out is somehow a Higgs particle, a Higgs boson or not. And you have to somehow differentiate the 2 things from the signal that you get from the detector. So the detector is basically a table generator. It makes 30 columns of data, and you have to say Higgs or not for each row, right? That's my math machine learning problem. And Kaggle picked up on it, and there's a Kaggle challenge on the Higgs boson. And of course, you guys are welcome to participate. Maybe I'll submit something real quick. It's only like 10 more days or so. You have to be really good to beat these guys, because whoever participates there wants to win, of course. They're all pushing hard. So let's see what we can do. I'm not promising anything, but we'll see. All right, so Higgs binary classification, we know that. What's the best method? Well, physicists think boosted decision trees, right? Makes sense. Random forest maybe. Neural nets. That's the state of the art. But the physicists have to add derived features first, which means my detector detects an angle or speed or momentum or energy, whatever, something from these particles flying all over the place. They have to compute from these numbers certain other numbers, features, derived features, with squares, with exponential functions, with sine, cosine, all kinds of stuff that then gives more data from the old data. And then you have more data, and you give that to a GLM or to a random forest, and it has a chance to do something with it, because only physicists know what a linear model doesn't know, right? Maybe not. Maybe someone else can figure out everything from those low-level features. Well, let's see. When you have low-level features only, there's a data set you can download here. If you have low-level features only, there's 21 of those. You get these numbers, AUCs. You know what AUC is? Who knows what AUC is? It's the area under a curve. The curve should ideally be like this. So the area is 1. If it's like crooked like this, then the area is less than 1. It's like half. Half would be total random. So you want to be 1 and not half. So the more zigzaggy, the more square the curve is, the better. And it's basically saying how well can it go up instead of to the right. Up means I get it right. Going right means I get it wrong. It's a false positive and a true positive. So you just want to get as many right before you make any mistakes. So that's the curve. And basically the area is only 0.6 if you have a linear model on the original features, which means a linear model is not that great. From all these detector features, can't really tell anything. It's almost random. Once you add these extra features, it's 0.7. It's a lot better. But 0.7 can be done with the random forest already on the original features, right? So you see that there's a boost every time you add more features, it gets better. So that's what physicists do. They get these numbers, 83, 84, and that's actually pretty good. You can say, I'm done, I found my Higgs, right? However, people are never happy with what they have. They always ask, can we do better? And especially since deep learning came to the stage, they're saying, well, can deep learning do better? And there was a paper just this July here published in Nature that says, let's do deep learning for particle physics search. And what did it find? I'm not telling you, right? That's the whole point here. We are going to find out. We're going to find out exactly what deep learning can do for particle physics. 0.73 is what they had as a baseline here. You see that? We've got 0.75, 0.76 up there. So it's close. We're a little better than the paper. Doesn't mean much. They might have just taken the basis, simple implementation somewhere. We, of course, have H2O, which is distributed, which is powerful, has the best math in it. So yes, we win against the Nature paper in terms of baseline performance already. So we could give them an 84, where they only get an 81. You see that 81 in the paper? So we already have 3 points more, just out of the box. 5 minutes runtime. That's not bad, right? But we can do better, of course. So let's figure out what we can do. Let me show you H2O. This is a 10-node cloud that we have with H2O in it. That's running right now in our office. Let me make sure it's live. Yes, it's using my phone as a Wi-Fi device. Hopefully that's fast enough. So we have 10 nodes. They're connected with 10 gigabit Ethernet, so it's reasonably fast. They have 256 gigabytes of memory, but I only give it like 30 gigs each, so it doesn't need that much. Deep learning doesn't even need more than 1 gig in this case. And here you have all these different model builders. Here you have the data. I can see view all, and I can show you the Higgs data set. It's basically 29 columns, 11 million rows, and takes about 2 gigabytes on disk. It's all doubles. There's this thing. You can compute a summary now if you wanted. Yeah, why not? We can say summary. And just right now we did 11 million rows, 30 dimensions, summary for each. What are the histograms, and so on, the percentiles, quantiles, everything. So that's pretty good. But we're going to do more than that. We're going to run deep learning. So deep learning, you don't know what it is yet, unless you already know, of course, but I will tell you what deep learning is in a second. But let's just say we use it as a regular classifier. We exclude the last 7 features, the higher order derived features. We don't need those. We let deep learning deal with it and see how well it can do without having those features. I'm going to do a grid search, 2 different network structures, network topologies. Let's not worry about that too much. It's just some parameters. Basically, mostly is either not active because you don't need to set it, or it's just default. So it's all fine. I'll just say go. And now you'll see a grid search starting. That's live right now, right? This is 2 different models, 4 hidden layers or 6 hidden layers. And you see here at the right side, there's a key. That's the long key that goes in the KV store that says under this key there's a model. And these are like 5 megabytes of model or something under this key. And I'm going to not look at this right now. I'll look at this one here. This is the first model being built right now as we speak. And you don't need to understand what this means yet, but there's some accuracy, there's some curve. It's already at 75. That's not bad, right? 75 was pretty good as a baseline. We go back, and we'll check with this stuff later when we get back. That is the baseline. 75. You just beat the Nature paper in these last 5 seconds. Yes?
Is the ROC on the test sample or the train sample?
Good point. That's on the test sample. So there's 11 million points, and when I started this, let me show you. When I started this, the model parameters say here, the training data set is part 0, which I split up into 10 million, and there's a validation data set, Where does it say validation? Oh, I don't have a validation yet. This is just reported on itself. You're right. As the model is building, it reports it on itself. But we're not going to ask this guy, what are you? We're going to ask later a scoring engine, what are you? So you're right. This is, you could say this is not right. It's true, this is wrong. But the number will be very close because it's 10 million points. They're all the same. The model only has a few hundred, maybe a few thousand parameters. So it's not easy for it to memorize everything. It can't overfit, right? Not that easily. But you're right, that's a good point. I used to run it with the validation set so I could see what, or actually a test set. I split it 3 ways. 10 million, 500K, 500K. So I run training on 10, test on 500, and then at the very end, validation on 500, and then at the very end I will test on the last 500, which I never looked at. That's my final number. So that's what I did in the past. This is just to run it on the training data only. All right. All right, so we'll figure out later how it goes. So deep learning, what is it doing in the meantime? It says deep learning is only deep learning if it's deep. That means multiple things, multiple what? Multiple layers of nonlinear transformations. So your model has to make nonlinear transformations and another nonlinear transformation from the original data. Anything else is not deep. And Facebook, for example, is using this pipeline of nonlinear transformations to detect facial features, right? And then say, okay, this is a large nose, small nose, this and that must be this person. And they get this done with 98% accuracy, as well as a human.
Could you perhaps give an example or two of that nonlinear transformation as a tool?
Yes, I'll explain that in the next slide, yes. So what is not deep, before we go into how we do the deep models, what is not deep, linear models are not deep, right? Trivial, it's just a linear model, cannot be. Neural net with one hidden layer is not linear anymore, it is a nonlinear activation function, but it's not multiple of those, so it's not called deep. Deep, it's only if you have 2 hidden layers or more. SVMs and kernel methods also are not deep because you just put a template like a kernel somewhere and then you add them up. It's not going to be another phase of nonlinearity. It's only one piece of a kernel and then linear additions. Classification trees, random forest, boosted trees, not linear. It's not deep. They operate on your original input space. Right? Are you this old or this old? Are you employed or not? This and that. It's not going to change that number into something nonlinear. So they don't make new features. So deep learning is trending because somehow this new feature making thing works. And you better believe it, right? This is taking off. Nature's talking about it. Of course, everybody acquires everybody else who knows anything about deep learning. So Jan LeCun is at Facebook. Andrew Ng is at Baidu. Steve Hinton is at Google. All these people have written papers for the last 20 years, and now they're Jeff, what did I say?
Steve.
Oh, I see. Sorry, Jeff Hinton. So they're all gone, right? But they work for some company, and we might never see their work again for open source. Who knows? Let's hope something comes out of that. So here's the history. Since the 60s or even earlier, there have been efforts making these things better. And today, you can read this handwriting on the right side here. Handwriting, traffic signs, pedestrian detection, speech recognition, your Siri and your phone, all deep learning. Google self-driving cars, deep learning. There's a lot of deep learning going on. Oh, this must be my screen saying it's nighttime. So there's also commercial applications, but of course, they're all the same. In the end, they recognize something, right? Deep learning recognizes stuff, just like our brains. Let me turn this off here. Oh no, that wasn't right. There you go. Now Sorry about that. Okay, this is better. So, yeah, let's see what happens. Hopefully there won't be too many Terminators running around because of deep learning, but we get a better life, right? Cars drive us to work and so on, things taken care of without us having to get into dangerous situations. So deep learning means multiple layers, hidden layers, of regular feed-forward neural networks. That's what it means to us. Regular feed-forward, supervised learning, stochastic gradient descent, backpropagation. We do this in a distributed fashion, multiple nodes. Every core is lit up, multi-threading. And of course, we use all the latest research paper inventions, dropout, adaptive learning rate. You see it here, regularization. I added a little of auto-tuning so that you don't have to worry about the parameters. Yes?
So why wouldn't you call random forests deep learning? Effectively, you have multiple nonlinear step functions taking the inputs from the previous step functions, and you could call the intermediate values as features that get through other nonlinear step functions and so on. So wouldn't that be a multiple? It's not a sigmoid, or it's not a continuous nonlinear function, but it's effectively step functions, right?
I think it doesn't make up new features.
I mean, that's just
you always operate on your 20 dimensions or 30 dimensions, right? You're not making up new features on which you apply your thinking again. You're not saying, let's take age and income, make something new, and then decide again. You're just saying, now that my age of this is eliminated and my income of this is eliminated, let's see what's left. But you don't make up something that's called age square minus income. That's, I guess, what you really need for deep learning.
So would you define deep learning that way? If you are creating new features, then it is deep learning.
Well, the feature has to be nonlinear, right? And it has to be
Yes.
multiple steps
Right.
of these feature generations. So you
Right.
have to create features several times, and they always have to be nonlinear,
Right.
and you have to use those newly created ones to make,
Right.
again, the next
Right.
hierarchy, right?
Right. So you have 20 input predictors or features.
Now you
and
make
from those
500.
you perform the nonlinear transformations, and you derive new features.
Yes.
And then you
then-
consider this the extended feature set
Yes.
to bed your models.
Yes.
If you are doing that, then you are doing deep learning.
Right.
Is that how
Right. Yes.
you would put it? Okay.
Yes. Multiple nonlinear transformations, right, in
On
your
the
data
input
process.
features.
So you have 20 in, then you have 500, and then you have another 500 that are nonlinear function of the previous 500. And at that point, you can say these features are totally nonlinearly derived in 2 steps from the original features.
So another follow-up is that if you're building a model, in your training, do you start first with 2 layers, then you start with add a third layer, or how do you?
No, the beauty of this adaptive learning rate here is that you can just say I want 6 layers, go, and it'll just do it. That's actually what I started earlier, right? When I said run, 4 layers and 6 layers. These are running from scratch, 6 layers, supervised, just like a random forest. I just say train. Yes?
And I look at the list, it's more like the neural network with multiple layers.
Right.
Yes.
Pretty much
Yes.
same.
Yes, multi-layer neural net, that's it.
That's it.
Actually, in the theory, the neural network, even single layer, theoretically, they can, approach the theory result.
Yes.
Almost zero.
Right.
Infinity,
Correct.
You know.
If you have enough neurons,
Correct.
you can do it, yes.
Yeah, exactly.
Right. But you need a lot, and that's not called deep, because they figured out that deep can be better than a lot of resolution, right?
Another question is this deep learning, do you experience something like stuck in the local minimum when you do the training?
Yes, you can get stuck in the local minimum. And that's why you add momentum and stuff like that to get out of it, right? And you have model averaging over many machines. It also helps. So there's a lot of things you can do to not be stuck. And I've not seen it be stuck. Like you never see something that's weird and just gets stuck in accuracy and everything else gets better. You don't see that. Usually you get to that best performance.
Are the training methods gradient based, or do you employ like genetics algorithms?
No, it is stochastic gradient descent. Every point you ask what's wrong with me and you fix it. I'll show that actually here. See, this is where it starts. This is the real neural network. So you have age, income, and employment as your input features, and then you make two hidden layer transformations, and in the end you say, are you married or single? And that could be a model, right? That's a small, simple model. It might be right. So these are.
Arno, there was a question.
Oh, sorry. Yes.
How do you go for your particular problem? How deep the network should be, or how wide it should be?
We'll get to that later. Yeah. So in this case, you have these connections. These connections say how much does this neuron affect the other ones. That's called the weight, and that's a matrix. Each layer is connected to the next layer by a matrix, right? These are 12 connections, 4 times 3. So you have to know these weights. You need to know these 12 numbers. So your model is those 12 numbers, and another 12 numbers, and another 6 numbers, and then another bunch of bias values to offset those, because you want to have a constant value as well. So that's what the next slide will say. You basically, you're saying how many times the previous one adds to me, right? That's the question. And if I know that you affect me this much, and then you affect me this much, you affect me this much, you affect me this much, and so on, so on, so on, so on, so on, then I know what my value is at the end. And then I say, wait a second, that was just linear. Now I need to do a nonlinear transformation. So I need to add some nonlinear function here that I apply on top of the sum. This was the bias value to add. So no matter what you guys are, there's always a million in the beginning that gets added to it, right? Let's say, because I want always to be a millionaire. I don't care how much money you have, I need my million, let's say. So you can add this bias value in. Of course, it might be a bad prediction for single or married. Well, depends on which one is which. Well, I'm married now, so I'm happy either way. In order to get to these probabilities at the end, you need to make this whole chain here going through. And this nonlinear function here could be 10h, that's the smooth one. It's like a sigmoid function, just scaled and shifted. Or it can be a rectifier, which is just flatlining and then suddenly it goes up linearly. It's easier to compute and leaves more sparsity in the network. There's more zeros everywhere because it makes zeros. And every time there's a zero, you don't affect the next guy much. You can skip some math, so it gets a little faster. Yes? We have 3 nonlinear functions, and you have to basically tune and see which one is better. You get some intuition, but I don't trust intuition much. In the end, you have to do a grid search. So if you want to know which one is better here, of course 10h is smooth. It means it's going to be able to do a square root function better than just a straight line, right? But if you have 1,000 of these straight lines, they can make up the square root function. So you need to know how many rectifier units you need to make up a square root, kind of. If you need to make up a square root, maybe you need to make up an exponential function, then you only need 3 straight lines and they go up straight. It's much better than to have a lot of sigmoids going up, right? Or maybe the prefactor of the sigmoid has to be higher or whatever. You have to like add this all up, and it depends on the problem. So you can make up your academic problems that's something difficult, and it will be tough with one and easy with the other, or vice versa. But in practice, you need to just play with it. Yes? First you, I think. Sorry.
So are the nodes using the same activation function, or they can?
Yes, they always use the same. In theory, you could mix and match, but I haven't. Yeah, it would be just one line of code somewhere to change that. But for the user, the input gets ugly, right? If you have 6 things, you have to get six numbers. But when you do it programmatically, it's probably fine. So this wouldn't be a problem. Yeah. Yes.
So this is purely from the experience-based question. Since as you keep on adding more and more independent variables in your model, if you keep on adding more and more hidden layers, number one, the model becomes so complicated that additional lift sometimes it does not justify actually in terms of actual making your model so complicated. And second thing is performance definitely hurts as a result of additional complexity. Can you just give your thoughts in terms of how do you find where to find balance, and what do you see as compared to going deeper versus still using a basic method, let's say that kind of forest should be?
And I always start at the bottom, right? I start with GLM, that's super fast. Then I do a small random forest, I get a baseline idea of what's possible. And then I do a GVM. And then I do a neural net that's shallow. And then I do a little deeper one. And then I have like 200 units or something. And I don't do 5,000, 5,000, 5,000 right out of the box, right? I'm going to start with something small. And if I know I'm kind of stretching it, or when I'm beating random forest by 1% or something, then I can say it's probably good enough. I mean, I don't have this pressure to deliver models, right? I make the tool, and you have to decide how much your time is worth versus how much your model has to be perfect. So I guess it's hard to say, but I would start not just grid search brute force, but I would say start with a comparison to other models first. The goal is that deep learning should beat them all if you wait long enough, right? And now the question is, can you beat them not waiting long enough? Well, sometimes yes, but you have to always find that point in the operating point, basically.
So one additional question, I'm coming from the financial industry, and a lot of time we need to explain to regulators in terms of how the model was actually predicting.
Yes.
Can you just help us? Do you have tools within H2O system in the sense of explaining how that variable is contributing to the overall prediction?
Right. So the only thing you can do here is basically a variable importance computation, where you say these weights are so important from age to all the others that age matters more than the income, and somehow you can connect these weights and compute an importance based on that. And I'm doing the method by Gedeon, which is some say is the best, according to a blog somewhere at SAS. But there's different things, right? If you have two features that are the same, they're correlated. You look at this one, not important, because if you drop it, it's still good because this guy is here. If you drop this one, also not important. But if you drop both, it's all totally bad, right? So what does feature importance mean? They're both not important. Should you drop them? No. So feature importance is not always an easy thing, right?
So these layers, can they operate in parallel, or does, as in the case of a neural network, does each layer have to depend on the result from the previous layer?
Yes. So when you come in with your point, age, income, and employment, your numbers get propagated through layer by layer. You cannot compute the last number without waiting for the other layers to propagate forward. That's why it's called forward propagation, actually, how this is moving through.
So where is the parallelism coming from?
Because you have many points to train with. And you put your point through and say, oh, I'm wrong. I'm actually going to explain to you how this is being done. So the next slide will explain that. Why don't we get back to that? Yes?
Is there a way in the view to extract the features which are different layers? I want to extract
that's a good
layer.
point. Yes, I can add that at some point, or you can add it. Anybody, this is available in the code, right? There's a logic somewhere you could say, give me what's in there, but it's not exposed to the end user right now. There's no API for that.
One more question. So people in the 90s did a lot of research also on adding feedback loops.
Yes.
So you
don't have this stuff.
You don't have feedback.
There's more things you could do.
Okay.
So in the interest of time, how?
Very quick.
Okay, go ahead.
Does the independence, the natural independence of the inputs improve the results? If you happen to be lucky, the variable is more independent, less linear.
Or is it better to have really orthogonal input than to just have? Yeah. Question is it better to have orthogonal inputs instead of just all collinear stuff that in the end doesn't mean much? Yes, I would say so.
You get better results naturally.
Yes. But I mean, if there's any differentiation, this should pick it up, right? The goal is that this will learn anything that you can learn, and it's all standardized. That's actually the slide, right? It says whatever your data is, it automatically gets standardized. If you have 1 million income, I have 10,000 income, it's the same thing, right? The numbers get standardized. Of course, not exactly the same, but it's not gonna. Actually, that's a bad example. If you have 1 million and I have 10,000, you still have 100 times more than me. But if your age is 10,000 times less than your income, doesn't matter because both are within 0 to 1, right? I'll make those per feature standardization pre-processing steps so that you don't have that problem. So anyway, so if you have employment status part-time, that just means that you have to make 3 numbers here basically. One is part-time, one is like full-time, one is self-employed, one is not employed. And you can make up these categorical things into numbers so you can actually do math with them. That's one thing. Another thing is that how do you initialize those weights? You can't just say they're all 0 in the beginning, because if they're all 0, then you can't really learn from it. You have to have some noise in the beginning. So this noise is created by some smart scheme that says based on the number of neurons on each layer, that's the expected multiplication weight overall, so make a little less if there's more and so on. There's like math that does that. It's all just straightforward. So once you have these numbers, you make a prediction, you say, okay, 0.8, I'm married. That's the number that comes out at the end. The number, just to be sure that you understand that, the number was made with the softmax function here. The last step is not 10h, the last step is softmax, which says basically exponential function of the value divided by the sum of exponential function of all values. And then you get basically automatic normalization between 0 and 1, just like a weighted sum exponentiated. It's all good under statistical interpretation. You get numbers between 0 and 1 and you're fine. So you predict 0.8 and you know it should have been a 1, so there's an error. How big is that error? Well, it's 0.2, but what does it mean? Well, it's probably better to say it's squared error or something, because you could be on the other side of, like, sometimes you have to do a regression problem, right? You don't want to have negative or positive be an issue, so you're just off. So you do a mean squared error. That's used for regression. Cross entropy is used for classification, because you're saying you should have been a 1, but you were not. How much were you off? Well, I'll penalize you the more you're off. Like if you should be a 1, then you're good. If you're a 1, and if you're not a 1, then your penalty is high. This goes up like the logarithm goes down. So this is pretty strong penalty for not being 1. That's what we use as an error term. And this error term actually goes back and propagates. The way it propagated forward, it propagates backwards. And that's an invention that was very helpful. As soon as you see that you're wrong, this point came in, made a 0.8 instead of a 1. It fixes it up. The whole network will get changed by this 0.2. And 0.2 says, well, I'm 0.2, I should have been a 0. Because I'm 0.2, my error makes it down this network. And then there's a number here, and then that number propagates to all the others, and in the end it adds up just like as if you had computed the actual gradient of the total error with respect to each weight. And you can change each weight. I don't know whether you saw that, but the goal here was to say, if you're here and you should go down here, you must change the direction of the weight such that it goes down with the air, right? Which means you have to basically follow the gradient. That's gradient descent. Go down, not uphill. And going downhill means you need to know the gradient so that you know which direction to go and how much to go. So there's a learning rate there that says how much you're following down that gradient. If you go too much, then you go up again. So you have to like balance all that. So there's all these little things. It took like 30 years to get it all right, and now we're at the point where it finally works. Everything's good. So backpropagation is a bunch of partial derivatives and stuff that propagate themselves forward. So you can follow the math if you like, but it's all just a detail. It just works. So this you do in parallel. You start with a model on one node. Each of these blocks is a node. And you say, okay, my other 9 nodes also need that model, so I send it to all of them, but I don't send it 9 times. I send it to my neighbor, he sends it to 2 more, and so on. It's a logarithmic broadcast. Then all these guys are saying, okay, I have a model, but now, well, train on your data. Every machine has data. Maybe it's the same data, maybe they have a piece of it. It's all configurable. So once you have your data, you say, okay, point, age, income, employment, propagate, figure out what's wrong, fix it. Next point, propagate, figure out what's wrong, fix it. And you do that, every thread is doing that on its data. And it has maybe a few thousand points at a time, depending on that's the H2O infrastructure that Cliff and others worked on. Basically make this fast, right? Each thread says, okay, give me 10,000 points, I'm going to just do that and nothing else. And the other thread does the same thing on different 10,000 points, and they all operate on the same weights. That's the key here. There's only one model per machine. Each machine has one model, and they say read the weights to propagate and then fix the weights. And we all are fixing the same weights as we fix the model at the same time. That means we don't have any locking, nothing, and that's a bit of a race condition if you like, but that's fine. You don't really hit each other too often, and even if you do, it might be a good thing, right? Who knows? You get lucky. That's the local minimum you avoid, basically. You just add a little noise. Yes?
All of this is happening in main memory, not in cache.
Depends. Well, the reads, of course, if you have a little matrix and you read it once and then it fits in your L1 or whatever, then you have a few more thousand numbers or so that you can read, right? You don't have to go to main memory every time. It's not random access, but there's some random access, of course. There's a lot of cache misses that happen if you have 30 threads saying give me this, give me this, give me this,
that's what I was thinking.
and you have a 4 million weight matrix, right? That's 60 megabytes or something. You'll end up in L3 on main memory a lot. Yes. So that's why GPUs are good at this, because they have faster memory bandwidth. Correct. So once you have a new model, then that's your model, right? Your machine has a model. Every machine is a different model, that because it saw different points. It saw a different order of points, different points. They just have a different model, and now they get averaged. And in the end, you have one more model in the end here that they all have, and that's the one that goes back into the KV store. And when I say show me the model, that's the model I see. It's always synchronous, and that makes life easy for model management, termination, cancellation, and so on. And that's not a problem yet, unless you go to 10,000 nodes or so. If this was supposed to be a 10,000 node solution, you probably would do some more asynchronous stuff of several workers that go work in parallel without ever communicating. And they only update from time to time in some peer-to-peer fashion, let's say. They don't have to do it through this. This is perfectly fine for us. So you can say actually how many points you should process in this step here. That's called the map, and that's the reduce. And this map part, you can say how many points you want to operate on. You can say do 10 million points, or you can say do 5 points. And it doesn't matter how big the data set is. You can say a fraction of it or a multiple of it, whatever it is. It will just keep processing points. Yes?
So is weight only averaging once after all it's done, or like it's actually on a sort of output there's sort of iterations that you have the averaging weights?
This is one MapReduce step, and then that happens over and over again. So this whole thing repeats. So this is the updated model, then it starts at the top again. It does it again and again. So there's a send, broadcast, work, reduce, broadcast, work, reduce. Every time you have a new consistent model in the KV store, you can also score it. You can say, how good is it, right? And then display that in the web page. By the way, our product is a web server. In case you don't understand this concept yet here, every time I show you a web page that says H2O or something, that is not our website, that's our web server inside H2O. H2O has a built-in web server so that you can talk to it. Just like if you send a REST request from JSON or something, then you can control it from your iPhone, for example. I actually check it quite often when I'm somewhere else, like is my model converging or not, or how well is it converging. I use VPN, right, and I log into the web server of the product of our cloud. Yes?
So, in the very beginning of your talk, you talked about your network being a 10 gig network.
Yes.
And based on what you're talking about, we get that you know what you're doing. So why only 10 gig and not 25 for InfiniBand?
Well, it's our own little cluster, right? We are a 20-man startup, so we don't have an InfiniBand system.
But I'm correct.
It would be nice, yeah.
Okay.
I used to have like Cray, the Connects, whatever, HyperTorus, and InfiniBand was slow, right? And now I would say, great, InfiniBand.
Yeah,
I'll take it.
We'll take the... So I bought my Mellanox switches on eBay, right? So I waited. The first one took me 2 years, right? But they eventually, you watch it and it goes down because they just want to get rid of it. So
basically the key to better accuracy is not just that you have, okay, go ahead.
So I didn't get the connection, so you said there's no locking, everybody sees the same thing, but at the same time you also said that there could be some race conditions. So what is the condition? So,
yes, there is intentional race conditions basically. So you say what's the number when you do a forward propagation, and I say back propagation, I'll fix that number, and I'll change it just before you read it. Well, then you get my new number, right? That's fine. And then you write it back based on what you thought it should be, and then you write something else back, and then that's what it is. It doesn't matter. It really is just everybody does the best effort. All the threads just racily update the weights. And it's roughly good enough, let's say. I've never seen anybody say it's a problem. Actually, this is a big step forward because you don't have lock contention. Imagine you have 32 threads all locking on every single number. That would be horrible, right?
So it's property of the...
Yes,
so,
it's called Hogwild. There's a paper called Hogwild with an exclamation mark that shows that this is good. Yes?
So each of the node, the W that you showed before, has a partition of the weight.
Yes.
How is that partition?
No, the data. The weights are shared, right?
The weight, everybody has the weight
Everybody
of
has
all
W,
layers.
and they all have W. Then they become W4, 2, 3, 1. They become different W's because their models are trained on their local data.
Yeah.
Every machine has different data, or they have all the data. You can also give all the data to everybody and say, I just want to have 50 MNIST models or something. Everybody trains MNIST on all the data, but I have 50 machines. It doesn't matter what data you have. All you need to know is that everybody trains on a different subset or on different data. It doesn't like they just process a random subset. They're almost doing like bootstrap sampling, if you want. They're taking a sample of the local data. Whether the local data is all the data or just a piece doesn't matter to the algorithm. It's just processing data.
So you have all the weight on all the layer? That's what you're happening?
Yes. Every machine has the entire neural net. The network is only a few 20 megabytes, 100 megabytes. Right?
It depends how many neurons you have, right?
If you want to simulate the brain, then you can't do it, right? Then you would run out of integer limits of arrays and stuff like that. Yes?
So on the implementation, you guys don't use any concurrent classes or anything, right? Because you don't care about collide.
Yes, correct.
So, but Java will throw errors when you do it that way.
No. It's just it's a floating point array, right?
So you let it just...
you just read it.
So how do you avoid the lock? Because when you, at a Java level, when you're writing to something, when you're reading the same value, Java will throw errors unless you write concurrent, right? How do you handle that? Probably...
Yeah.
So you only get an error if you have some sort of structure involved for which you have to do consistency. In a big array of floats, there's no requirement for consistency to avoid crashing in that sense. So it's just a pile of numbers in memory. One core writes, one core reads, next core writes, next core reads, back and forth and back and forth. That's not any kind of error or crashing condition. Now, the value you pull out at any given core is one of many writes that happen.
Okay.
It's literally a float array.
Okay.
And there's a bunch of numbers in there, and then every thread says reads at index 7 or 5 or 20.
The float write is atomical.
Sorry?
The float write is atomical.
The lowercase floats, not uppercase floats, also, right? There's no uppercase anything. It's all like fast Java. No garbage collection issues. There's no big anythings, right? There's only a few real Java objects that we make that live like as long as the whole model lives or something. There's no stuff allocated, deallocated. Not much to clean up. We have our own cleaner as well. We clean up even better for the stuff that we need to clean up in the KV store. So basically, once you have this adaptive learning rate, you can learn. For each neuron, there's a learning rate that says how much I follow the gradient. That rate to update the weights, that rate is adaptive. Time dependent for each neuron. So if you have 5 million neurons, you have 5 million logic things that keep track of all that, but it's well worth it. In the end, you can really train fast, and it converges always. You don't need to worry about it. Regularization helps a lot. Dropout is good. Dropout says I don't see everything, and hence I become better against overtraining, overfitting, because I don't need to know that you have a green T-shirt, for example. If you throw an apple at me, it might have been someone else with a blue T-shirt that threw the apple at me, right? I don't need to just look after people with green T-shirts, for example. But anyway, there's all these kinds of things that make sense, right? They're all just logical things, and they have been added time after time, and in the end, they all make sense, and it helps a lot. So grid search is a big one. Checkpointing. This is a detail on the learning rate, how this works. There's some rolling average, moving averages of the past. So if you change this weight a lot all the time, then you should keep changing that weight, and so on. There's like rules that figure out how to make this adaptive. This is the dropout thing. Sometimes just say, I don't want to know your income, I don't care, I just care about everything else. that's good enough. And the next time you give me a point, I will care about income again. Randomly, I just drop 20% of your input, for example. That's dropout. Yes?
So grid search you're doing for the number of levels for everything you do the...
You can specify the dropout rate for each layer. That's what the question was?
No, I meant my original question was how do you decide how deep the network should be or how wide it should be?
That's going to be in the next few, in the end we'll know more. I want to get to the point with the real data, right? We have more actual real data to play with. Then we can get some intuition for that.
These rules that you're showing us now,
yes.
Are they just empirical generalizations or are there a theoretical reason why they always are bad?
Well, this says I train exponentially many models because each model has different set of neurons, right? This time it's a neuron that doesn't have an income neuron. On the next time when the point goes through, it doesn't have a neuron in that layer, and then next time it's another one, and all these things get like memorized in the system, and then you have an ensemble of all these different neural nets that have different number of hidden layers and so on. That is a really good, like there's some proof, but you can't prove that for your data set it will always be better with this, right? It's kind of it's always some limit. Yes?
So one extra question about the race condition. So
the race condition.
That's introduced some randomness, right?
Yes.
So you see that if you run it multiple times, that's
yes.
the result.
If you run it multiple times, you get multiple results, but they're fairly close. If you want it to be reproducible, you can run it on one thread, but then you need to have small data. And currently, as soon as we have more than a few megabytes of input data, we cut it up into multiple threads. So our system always parallelizes it. And it's always fast. So you kind of have a problem at that point. If you really need to be reproducible, you would have to change the source code somewhere to make it only one thread that works, which would suck, right? You don't want to be slow. So, locking, which makes it super slow. Yeah. Okay.
It's okay to be Q&A. I think it seems like
yeah.
an engaging audience.
Yes, it's great. So if anybody has to leave, please watch the recording later. But we have a couple more slides. Only about like 18 more slides. So this is MNIST. Who knows MNIST? MNIST is digits, right? Handwritten digits, and you want to figure out is it a 5 or a 7 or something, or a 3, and they look similar, 5 and 3, 2 and 7. They're all the same, 8 and 3, you write it fast. So which one is it? So 28 by 28 pixels, grayscale, they make it like standardized. That's the guy who went to Facebook, Yann LeCun. He's been the proponent of doing deep learning stuff for the spatial recognition, and in the original days, of course, it was just text recognition or letter recognition, digit recognition, step by step. This is basically the beginning of everything, but it's also still the benchmark. He says, anybody who claims they know stuff, don't trust them, ask them what they do on MNIST, right? That's what matters. So let's do that. 60,000 training points, 700 features. That's 28 by 28 pixels. That makes a long vector of numbers, 0 to 255 for each point, grayscale. Is it black or white or gray? And you just wonder basically what is it. And each point gets processed through that network. And the world record right now, without doing any convolutions or pre-processing of this data, you have 60,000 rows, right? What you could do is you could say, okay, I'll turn my 5 little left, right, I'll make it a little bigger, a little shift it up and down, I'll make more data. That way you have more training points and I can get smarter. No, we just use the 60,000, nothing else. No distortions, nothing. And no convolutions either. That's something we don't yet have. But it's basically something that's really good for image detection. It's looking in Fourier space. That's what your eye is doing. It looks in frequencies instead of just pixels. So it's actually a good thing to do. We don't have that yet, but this is on the outlook basically, in the list of to-do things. If anybody here wants to pick that up, that would be great. Other than that, let's move on. So 0.83 is the current world record on this method, and we get 0.87 after 4 hours on 4 nodes. So I guess I could now, with the 10-node system, with 10 gigabit and all that, I could tune it a little longer and maybe get another world record here. But we get 0.87, and there's only a few things that are wrong, like the 4 and the 9 and the 2 and the 7. You can see that they get confused a little bit, but there's not much you can do at this point because the data set is just wrong, right? Somebody did write a bad 7 and a 2, that's just what it is. So you can't go much below that. We get the world record number basically. And at this point, the second digit doesn't matter that much. There's only 10,000 test points. So there's statistical noise. So you're going to fluctuate. It's 87, 83, 85, 89. It's just going to fluctuate. So I guess I'll run it some more to get an 83 by luck. And then I say this is a weather data set. It's super small, just to show you categoricals like this, like rain, up, down, small, early AM, PM, whatever. This stuff can be taken. You can say run, do 5-fold cross-validation, for example, and it will show you the AUC curve. That's what I mentioned earlier. So this is the curve where you want to be as square as possible. And we have all this in our web API. So I can show you that real quick on my laptop. So here, localhost. Okay, so now because I rebooted my laptop, all I have to do is start the Java IDE and say here, this is how I run this. I just say load data sets, and all this does is loads prostate, weather, and MNIST data sets here. And now we should be able to go back to the web and say load, yep. And now I can say, where is it, run weather, for example, here. So I want to predict whether it rains tomorrow. I ignore the date and this number here and the last number. That the authors of that data set said ignore that. I do 5-fold cross-validation and I say go on my laptop. So basically it doesn't matter what the data is, right? It could be anything. It can be pixels, it can be text, it can be well, insurance, fraud, it can be marketing data, customers who bought what, when did they churn, are they going to churn, whatever it is. So here you see this model. This is not the n-fold cross-validation result yet. This was the main model was built on the training data. And now here we go, 15% error. It built these 5 other cross-validation models that each were built on an 80-20 holdout split, right? 80% for training and 20 for testing. And then it would stitch together those 20% pieces to make a prediction on the original data set. So there was no other test set at the beginning. All it had was a training data set, and then it did the self-holdout stuff. So for those who know machine learning, this is standard. We support all that. We see, again, this is just a small little network, 11,000 features, anything. But this is already very powerful because you can do stuff. Of course, random forest will be fine tool for this kind of stuff. Anything that's small runs fast anyway. But the point is to show you that this is interactive and you can do whatever. And even on the cluster, it's interactive. And yeah, this is a grid search that I wanted to mention. So I showed you a grid search earlier with the number of layers. You can do the grid search with anything. So for example, we go back. I say do the same thing again. Let's not do folds this time. Let's just do a training data set and measure the performance on the training data. Who cares? Just tell me what's my training accuracy. But now I'm going to run, let's do only 100 epochs for speed, and then I do different like adaptive learning rate numbers, right? Something like that. And different input dropout, and different L1 penalty. Anything in R you can specify even the categorical things like what's the activation function? You can say this and this and this. Just C, open paren, this, comma, this, comma, this. You pass the whole list, it's going to automatically make a grid search over it. And you'll have a whole matrix of stuff being run.
So is that grid search done on those specific parameters or a
Yes.
range between those? Okay.
It's not using the Monte Carlo sampling approach where you get better. This is still the stupid grid search. It's just purely Cartesian product. But we are planning to add this randomized search where you say from here to here, do 10 tries, and then this dimension here to here. And once you have more than 4 dimensions, it pays off a lot to do that. So in this case, this one was the winner, and you can go ask what was it. Here, oh, I see it was 0.99 10 to minus 8. This was the text. That just happens to be the default as well, by the way. So here you go. Default values were fine. Of course, this is small data, so you have to run it several times because this is on the multi-threading, right? Race conditions only have 11,000 numbers and 8 threads, so there's some noise in there. So normally you want to run bigger problems than that. That's just a joke. But it's good enough for live demos. Just kidding. We'll do something better right here. This is eBay text classification, 500,000 rows, 8,000 columns. So that's a big data set with all just zeros and ones, sparse data set. How do you handle a sparse data set? Well, you just take it in, right? Neural net has no chance to do anything smart because there's all noisy weights everywhere. All the weights are filled up. So now you're saying there's a lot of zeros coming in. Sure, well, then you don't need to multiply those. That's fine, you can do that. But then once you come back and you need to update the weights, you still have to update them all. You have to fix them all. Unless the gradient is really zero locally, then you can skip some stuff. So there's sparse stuff doesn't help a whole lot, so it's still going to be slow. But all the shortcuts that are possible are implemented. It's trying to be as smart as it can to be fast. And in this case, what do you think? 400 output classes. It's trying to say, from the description that was written by the user when they were selling something, what was it, right? Was it a gold watch, or was it a steel diamond, or whatever? Or what? Well, that would be a bad one. Was it a women's watch, or was it I don't know, but some jewelry? So only in the jewelry section there's 467 output classes. They want to know, eBay who does this, they want to know which one is it, right? They're using us in production, and they're using H2O for a variety of things. This was one of the early use cases last year, in October 29, that was last year. They were running on the Arno, of course maxed out. And the problem here really is 400 classes. Figure out what's going on here. And if you tell that to a random forest with 8,000 columns, or a boosted tree, even worse, go through all the dimensions, figure out which one is going where, make all these splits like this or not, this or not, this or not, it's going to kill you, right? So this is a lot better. And that's what you see. You get 88% accuracy, 11% test set error. After just 2.5 or 3 hours of training on 4 nodes, you basically get it almost right all the time, 90%. There's a hit ratio that's computed. Where is it here? The hit ratio, 95% hit ratio in the top 4. So you can give the user a list, say these are the top 4 things, and 95% of the time, or 96 almost, it's going to be the right one. Right?
So here did they do 400 and something, 67 different binary models?
No, not in deep learning, right? There you just have 470 output neurons. It's actually fairly cheap, because all the other neurons here, if you look at these numbers, they're a little small here, that's 8,647 input neurons. Then 1,000, 1,000, and 1,000, 3 layers of rectifiers that drop out, and then 467 in the softmax, which means whatever the number is, that's what it is. And then you say softmax, right, which says exponential function of this divided by the sum of exponential function of all the others, and then the winner will win, basically. And whoever had the biggest number, that's what I predict. That's the right one 90% of the time. So that's pretty impressive for like this multi-class thing. There's not many tools that can handle multi-classes much better.
The definition of 467 classes, that's done by human before any of this. That's pure business.
Yes, this is supervised based on something, right? And in this case, something was probably what the human said it was when they posted it. But it might have been cleaned up by somebody. Maybe this was a cleaned up data set where they made sure it's really good or something. I don't know what the standards for this time, but there are also going to be a lot of errors, right? Maybe there's a lot of errors and you never get better than 90% because it's just wrong or something.
Is this public data?
No.
eBay data? No?
It's eBay data.
They gave it to
They
you?
gave it to us, and we're allowed to talk about it. So this would be a nice example. By the way, this data set was 18 gigabytes as a text file, but when it was loaded into H2O, it was only 60 megabytes. Now you wonder why is that? How is that possible? Well, we use compression. We use lossless compression. That's one thing that I didn't mention in the beginning. That's another secret thing, or not secret, but a really good thing that we do, which is it's it compresses stuff as it comes in. When you give me a number, 5, 7, 18, 25, I say, well, I need only 2 bits to represent those numbers or something, or 4 bits, or 6 or 8 bits, whatever. There's a couple of, like 15 different compression strategies saying, oh, it fits into 16 bits, or you give me numbers from 10 billion to 11 billion. Normally you'd say, oh, that's too much, it's a double or something, or it's a long. No, it's only 1 billion different things, and that fits into a 32-bit, right? So even it's 10 to 11 billion, it's still a 32-bit number. So we can compress stuff, and we do that losslessly, and we get it down to 60 megs because a lot of zeros, rung length encoding, we say just store the non-zeros and so on. There's a lot of tricks you can do to compress stuff. Obviously, sparse data set should be sparse, right? Nobody wants to store this tens. Yes?
But in this case, what was one data point? Those many columns?
One data point was what the user entered when they submitted the eBay post, and it was transformed by word2vec into a binary vector of features that we don't know what they are. Something like, was it this or not, was it that or not, and so on.
Some engram based
Yes,
something.
right. What words I used or something.
Text description of an email.
It's another machine learning method basically to make a vector out of text so that you can process it.
A huge number of words that can come in here.
Yeah, and they ran to word2vec, which created some magic features.
Oh, okay. So you don't use the word2vec.
We do have some unsupervised stuff, and I'll show you that soon. Oh, sorry, the question was, do we have unsupervised, or is everything supervised? Yes, we do have both. But we don't have pre-training yet that you can use as a user on the outside, so layer by layer pre-training. That's one of the JIRAs that anybody is welcome to work on, but that's one of the things one can do. And I've done it in the past, it just hasn't been exposed as an app that everybody can use. There's all these things, right? You can do it as a quick hack in Java, or you can expose it to the world and say this is how we do it, and then it takes a little more effort. And we're going there, step by step.
Or you can hire.
Exactly. So this, by the way, is not tuned, right? I didn't spend a lot of work on this. I'm not the data scientist spending time modeling stuff forever until it's good. I don't have the luxury, unfortunately. I would love to see I can get this down to 8% or no, 5%. I'm very competitive that way, but somehow I just run it and then I say, okay, it has to be good enough. Next thing. And so here the next thing is scalability, for example. So we ran it on 64 nodes, one of which was dead, so we had 63 nodes. Now all my scaling plots look a little weird. Anyway, I'm not showing the log plots as we used to do in HPC when you go all the way up to 10,000 nodes, but it still shows you that you get a speed up of about 30 something when you go from 1 to 60 nodes. And you say, well, it's not quite 60, it should be 60, right? When you go from 1 to 60. Well, actually, one node has absolutely no communication. 2 has communication. 4 has communication. So what you really should look at is 2 to 64, because they all have some communication, and you can see whether it's 30 times slower or not. So this was more like a marketing slide, but I'm sure you can understand that going from 2 to 60, being 30 times faster is still pretty impressive, right? This is parallel. This stuff is working in parallel. Now the better question you should ask is the accuracy going to be good if you run on 32 nodes, right? Because you average, everybody builds something and then you just average. Maybe you lose something. If you found a local minimum that's really good, and I found a different one, and everybody finds a different local minimum that was super great, and you just average it, it's all gone again. But we'll see, right? The results I showed you earlier was 4 nodes. That was pretty good already. And I'll show you more with the 10-node cluster we just got recently. That is a lot. I mean, well, we won't take anything before it's due time, but it works. It works. I haven't seen it not work. Of course, you have to make compromises, right? If you don't communicate, you can process forever, and then you communicate once an hour. It's not going to be good. You have to communicate every so often. So I added this auto tuning that does it like 2% of the time spent on communication, the rest is spent on computation. And it's based on some benchmarks for network speed and the actual time it takes and so on. It's all like, it's doing its best to adapt to what it can do, given the load of the system to be not too wasteful with CPU or network. So this is the anomaly detection. That's one case of unsupervised learning where you basically try to figure out whether there's an anomaly or not. And how you do that in deep learning is you're basically making a model of what's normal, saying my heartbeat should look like that. And in order to figure out how a heartbeat looks, I'm going to make it from 200 input features. Each heartbeat is 200 pixels, and one after the other. Each one is a row in your data set. They're just visualized like that. These 200 input pixels of that signal, those are going to be compressed into 20. I have a neural net with 20 features there in the middle somewhere. So these 20 numbers, non-linearly derived from the original numbers, those 20 things have to be enough to tell me what's going to come out on the other side. And what's going to come out on the other side is supposed to be the same as the input. That's what an autoencoder does. It tries to self-encode itself. You could say, why don't you just do an identity? Well, the point is to go through a thinner network in the middle so that you can do a dimensionality reduction. But non-linear PCA, right? It's not PCA. This is non-linear reduction of dimensionality into these 20 features. So once you do that, you can then make a prediction on this test set and say, how normal are you? Because I'm reconstructing my test set with this anomaly, I'm putting it through this network, and I say, I'm going to make what's normal, because that's all I do. My network has learned to make normal happen again. So it takes this and reproduces it into this. This is how it looks like after it goes through this network, and it doesn't look like the original anymore because it lost this little anomaly there. And if you compare the reconstruction with the actual test data, you see there's a difference. So this is one way to find outliers based on the nonlinear structure of the data. Right? Of course, this is not trivial. If you have a 500-dimensional data set with all kinds of stuff, how do you know whether it finds the right stuff or not? So this is an open research project still to actually make an application out of this that's bulletproof, that finds the outlier. You don't even know what an outlier is really, right? What is an outlier? If this heartbeat started going flatline after the next few lines, that would be a bigger problem, right? But how does this thing know what it is? So it's always difficult to put everything into this mask of what's normal. But the idea is that you train somewhat supervised basically on what's normal, but there's no labels involved. It's just data. You just understand the structure of the data. So basically this is an unsupervised method because there's no labels, but it's still needing a training data to learn what's normal. And then you give it something new, test point, and you say, are you normal or not? And then you get the reconstruction error back for each point. So we have this as an app today, if you want to play with that. You can use all these features from R. These are all the features in deep learning right now. It's a long list. They're all explained in this vignette that Viraj wrote up in August. And I helped him understand all these features, so that was a great bit of work. And we have a PDF vignette available under hexadata.com/h2o/algorithms. And this link will work, and you can just go there and download it and then follow those instructions. It has a example R script and so on, so you can actually copy paste that into your R studio and you can just run it. This is the nanosecond scoring engine I was mentioning earlier. So when you click on Java model up there on the web page, you get an instruction that says how to download it, and you literally get Java code that just does the model and nothing else. It predicts. It just runs the model as a prediction engine. It doesn't train, it doesn't do anything else. It doesn't split the data. You have to give it the data in the right way. But there is some pre-processing tools that we have to make the same adaptation from the original data to the data that you actually use for training. So you can, like the column order or whatever, it's all automatically generated. And we have R units that run, that actually download this Java code and compare it against the inner self prediction from the Java model in main memory, so to speak. So it compares the in-main memory solution with the downloaded and inlined L1 register solution, and they both match. And one is just much faster than the other one. All right, finally we're back to the Higgs particle. Oh, that was a long one, right? A long breather here. Well, so who has any guesses as to how well deep learning can handle this problem? So we had a 73 baseline. We saw that we got it to 76, right, with our random forest and boosted decision trees. Once you add the high-level features, you get to 81. We saw it got to 83 with our other methods, I believe. And if you just use the high-level features, it's actually better than just the low-level features, even though there's only 7 of them. That's really because they're meaningful features. So who thinks it goes above 74? Well, obviously we had 76 already, so everybody should raise their hands. All right, good, good. Wake up. So 77. 78. Who thinks it's going past 78? 79. Some confidence here. How high can it go? Do we get an 81? 83? Oh, that's a lot. Let's see what we can do. So let's go look at the web interface here. The thing we just launched earlier, this guy. This was the 4 network one. This got to, let me reload that because it was stuck at 1.6 epochs here.
So how many positives and how many negatives do you have in your signal, in your labels? Roughly the proportion?
Oh, sorry, it's a 53 versus 47%, so it's pretty balanced.
Okay.
I'm sorry, what was that question?
What was the balance between Higgs and not Higgs? It's a balanced data set. So this was the model that took 2 minutes to train. Let me make it a little bigger. 2 minutes to train. 100, 100, 100, 100, 4-layer neural network. A little bit of L1 penalty, L2 penalty in this case. Here you see the statistics, what are the weights, the bias values, standard deviation of those and so on. This is are the automatic learning rates, by the way. So you see that this layer has the biggest learning rate, and this has the smallest, and so on. They're all like different layers have different learning rates because that's adaptive learning. So we get down to an AOC of 78. That was in 2 minutes with this 4-layer network that's super tiny, right? We processed
785. Those of us that said 79, I think we win.
Yeah, awesome, 79. So 700,000 samples per second on 10 nodes. So it processes pretty fast, and you see the accuracy actually was already pretty good after 1 minute. After 6, even 76. So it beat all the other methods already after 25 seconds, right? So when somebody says deep learning is slow, it doesn't necessarily always have to be. It's only slow if you have a big network and if you have to go through all the data 1,000 times and so on. Sometimes the data is same, like every point is roughly the same anyway, right? You have 10 million Higgs, how much can they all be different, let's say? This is kind of a data set that draws from 2 distributions. Maybe they're not that difficult to do, but then again, this is the Higgs boson detection problem. Biggest experiment of mankind. It cannot be that easy either. So they got to 73 in all these years. We get to 78 easily. It's pretty cool, right? Enough. So now let's go back to the actual grid search, because we ran 2 models, right? There was another one, which was the one that was the winner, and maybe it's a different one. Yeah, this one is actually better. That's the one with 6 times 200. And it got down to 80 in 4 minutes. So it's another 2 points, just like that, in 4 minutes. So now let's see how high we can get if we do our best effort. And I'm actually running something right here. I had to stop this. It's the same cluster, it's a different port. So we have different ports. Each port tells me what cluster it is, so to speak. H2O cluster, right? My cloud is alive. I'm not running anything, but now I can continue. I can say keep training. Because we stopped the demo, we're done with that. I can say continue from this old checkpoint, do another 100 epochs, and process 1,000,000 points for each MapReduced iteration. I want each machine to do about 100,000 points, and then they talk again so that they don't average too infrequently. So this is now a checkpoint restart on a 10-node system. After it's already trained for 4 hours, now it's training some more. 90,000 samples per second. It just keeps processing. And who saw the AUC? Here, 86. Pretty good, right? 86 down here.
So, are you doing any cross-fold validation?
This is actually on a validation data set in this case. So this was not done with cross-fold. This is just the test set. And this is the test set. I'm basically cheating a little bit here because I'm using the final test set, the very last test set, just for your eyes here, to show you like this is what I get. In reality, I was using the split number 1 instead of 1. Like 0 is the 10 million, 1 was 500,000, and then there was another 500,000. I was using the validation set for the tuning. And now, at the end, once you found your parameters, then you test on the test set one time, right? And I'm doing this on the last one here already, part 2. This is the last one. So this is the final number. But actually, if I did part 1, it would be the same. We can actually do that real quick. We can take this model. What was it? 86.3, 86.4, okay? Who had 86 in their minds earlier? Not that many. Okay, good job. All right. So we say score on data set, and I just say Higgs part 1 instead of part 2. Okay, fine. Prediction. Typos are allowed. Let's make a typo. So now it makes a prediction, but it's also training, right? At the same time, it's training the model some more. So this is the last point in time that the model was put into the KV store. And every few, let's say every 20 seconds or so, it updates the model. And this is just the last time it was updated. So this is using whatever the model was at the time. I just made 500,000 predictions. And it shows you for each column, is it Higgs or not, based on the probabilities. And now we can use this prediction to make a AUC number out of it. So the actual one is the Higgs data set part 1. First label, the first column is the label. The prediction was my typo. And let's see what we get. 85.6. So this shows that there's a little bit of a difference between the two 500,000 splits, right? So if I had tuned onto this one instead of the other one, then later I would have been surprised how well I'm doing on the other half, right? So that's why in reality what you would do is n-fold, like you said. Who was it? N-fold, because then you get 10 or 5 different splits where you have 80-20 5 times, and not just saying, oh, the last 500,000 are what I used. But the paper used the last 500,000. Actually, what the paper did is they took the first 10 million, and then they only took 2.6 million for training. Random 2.6 out of the first 10. And from the last million, they cut it in 2, 5 each, and then they took 100,000 only for the actual validation and the testing. I think the testing might have been on all 500 at the very end, but for their cross-validation, or the tuning, they only did subsets of each split. But I took the same big splits, 10 million and 500, 500. So it's as fair as it gets. But of course, we have different methods, we have different activation functions on. They use 10H, I use rectifier. So it's basically roughly a toss, except that we have better numbers all across. Well, let's see, where is it? Oh yeah, I wanted to show you the scoring. While we're doing that, let's do some more interaction. Let's go back to this guy, where we just ran those models, right? When you look at jobs, you saw that I ran these big deep learning models. I ran some earlier, but I deleted them again so that they wouldn't mess with us here. That was just my practice run. So I ran a GBM, a random forest, a GLM, and so on, and now the 2 deep learning models. Now I want to see which one is the best. I'm going to go to score, multi-model scoring, and then maybe in the meantime, let's see, the other guy, yeah, it's fine. The other cloud is still up and running deep learning in the background, so it's a little slower, but it doesn't matter, we're still fast enough. Let's look at all the models. Let's score them all on the last test set, because they were all just built on training. There was no validation, there was no testing anything, there was just built on training. We just made a model, and now we're scoring them for the first time on the last holdout set, 500,000. And now you see these models here. You see the AUC is printed here, 76 for random forest, 59 for GLM, 75 GBM, 79 for the deep learning model with the 200, 6 layer deep, and this is the 4 layer deep one that has 78.
Can you run multiple models at this? That is, in terms of just jobs that these are running, can you simultaneously?
Yes, you can submit stuff and they just run in parallel.
Okay, so it will handle, like, if you have multiple jobs on
yes, you can submit random forest GBM at the same time deep learning, but of course it gets slower and slower, and also repeat for memory and all that. It's going to get ugly at some point, but usually what you want to do is each data scientist gets their own cloud and they can play with it, right? They can have their own R session connected to it and so on, and they have their freedom. They don't kill each other's jobs and so on.
So you say that you do some unsupervised learning.
Yes.
Do you do sparse coding, that kind of stuff?
Yes, that's used in this anomaly detection.
Okay.
So now we can do this comparison here. There's the visualization. You can see all these different models. You say which one is that, and it will say, oh, it's a deep learning model here. You can say, show me training time as x-axis and AUC as a y-axis. And you can see that this is the time to the right and the AUC up. So the longest taking one is the random forest here, and GBM. But of course, random forest was a little better than GBM, so it's fine. This only took like 400 seconds or 500 seconds, so it's only a few minutes. Doesn't mean that random forest is always slower, right? That's just the parameters I used to get there. This was the deep learning one that got to an 80, and this got to a 78 in those 2 minutes, or 4 minutes, whatever it was. So this is basically competitive timing with the other models, but higher accuracy. In this case, on the raw, low-level features. But let's go back to the comparison with the full models. Because I ran some over the weekend, right? I started this whole Higgs stuff last Saturday or Sunday in preparation for this. I said, let's see what we can do with Higgs. So this is not Nature paper effort, right? They had a half year or something for that. And we only had a few days. So this is not final by any means, but it's of course nice to know what they did so I can do something similar. But what else can you do other than a 6-layer neural net, right? It's not that difficult. I use mostly default parameters. It's all just make me 5 layers of each 200 or 300 or 500, and everything's automatic, and just say go, and then you wait 5 hours, and you come back and you get an AUC of 80 something, right? It's really automatic. That's what I want to point out here. It's not you need to know for each thing, program every line, everything has to be just like that. They're all pretty good, and you get good numbers out of the box easily. Otherwise, I wouldn't have been able to do it, right? Yes.
Can you understand the difference between the deep learning blue versus
yes.
deep learning orange?
This one was the 6.
This
one was the 6 times 200. And this was the 4 times 100.
And that is why the scoring time is very different.
The scoring time is just how long it took to make the prediction, as the cluster was totally busy, right? Because I did this screenshot earlier when it was training as well. So, but the training time was not busy. So this is roughly fair. The scoring time wasn't that fair, but you can get an idea. I mean, it was roughly loaded the same way for all these times it was scoring. So GLM is the fastest, right? It's just a linear model. And of course, deep learning takes longer to score because it has to multiply through all these weights. So if your time to score prediction is important, then you want to use something like a gradient boosted method. Shallow trees, you have less numbers to multiply. But only if it's accurate enough. If you need more accuracy, you need to have a random forest that digs down deeper. A deep random forest is very accurate. Also in this case, they're all deep, right? Both GBM and random forests are deep for this Higgs data set. They have to go down and memorize every little detail in the structure because you only give them the low-level stuff. They have to really see everything. So a shallow tree is not going to do its job well. In this case, you need a deep tree. So for deep learning, this is only small models. And now I'm going to show you the final numbers. So as far as I can say final after 4 days or 3 days. So this was the paper, right, up here. Show you. So this was the baseline of the paper on just the low-level features. And now they got it up to 88. And I haven't gotten it up to 88 yet. When we looked earlier, it was 80, what was it, 86 something? The one that's still running at 63. This one is running right now. Let's look at where it is. I expect this to finish somewhere in the 88s as well if I wait till tomorrow. Sometimes you get the L1, L2 penalty wrong, and it's overfitting or generalizing too much, and then you're basically taking a corner somewhere where you could have gotten a little more on the edge, right? Because you're smoothing it too much. And then you got only to 87.5, and you're like, no, I should have done one more grid search or something. We'll get there. I mean, we'll have to just balance the other requirements of our team, right? This is also used for Jenkins continuous integration tests. I don't want to use the machine just for doing Higgs search all the time. So here we're at 86. But this again is just for today. This is just to see whether I can get something going quickly. I started this 4 hours ago. This is not the fair comparison. This is just the number that you get one time shot. Ideally, I would run this on the part 1 split and then run a grid search and just wait 2 days or something. All right, back to here. So we see that we, instead of having 73 baseline, had a 75 baseline. And if you have all features, you get to 83. And now deep learning gets to 83 as well, easily, with 3 layers. So you're better than having all the human-made features given to the best gradient boosted method, right? Just by giving a 3-layer neural network that has only a few neurons to even do something. So the nonlinear features are super important in this case. And that is because this is physics, right? There's square root of sum of squares and stuff, and that's all smooth curves. This figures it out. This literally figures out these curves. And there are some of the parameters I used. So it's either 300 or 1,000 or 500 units per layer. They're not big networks. You can run bigger networks and probably get better accuracy. It just takes a little longer. Yes?
So do you change the adaptation rate slowly over time? You're doing it, right?
The auto-tuning currently is constant. It's like doing 2% of the time is used for communication.
Yes.
So what you should do, what I'm planning to do is say, as I converge slowly, more slowly, I need to update this rate to be more often in communication, right? I need to communicate more often. Or I need to just say fewer machines maybe is better or something. There has to be some kind of notion. If you have 500 machines and you average all the time, it might pull into 2 different directions. So that's an active research topic to how to optimize many machines in the final convergence. So if I had to run this on one machine, maybe the numbers would have been even better. Because many machines sometimes doesn't quite get there because they always compete with each other. But it's very close.
What about parallelizing the scoring of the function?
Oh, the scoring is already parallelized, right?
Like on different machines?
Yes.
It's alright.
So the scoring data set is 500,000. There's cut into 50,000 every machine, and then everybody gets the model sent to it and say predict with it, and then they make a prediction and send that back. It's already parallelized. So this one here, my goal is to beat the 88 soon. Let's see how we get that done. And this concluding slides, basically the tips are more layers gives you more nonlinearity. We saw that. It's very useful for Higgs. More neurons gives you more resolution for like MNIST, right? There you wanted to have 2,000 neurons to see all the 700 pixels. And if you add regularization like L1 or L2 penalty, you basically say the weights have to go to 0 or have to be 0. Basically, with L1, you basically drive it hard. And with L2, you say it's okay if you're not quite 0, but I want to balance all the weights a little. You don't want to let anybody grow too fast. And dropout is very important, but only if you have enough features so that you can afford dropping out stuff. If you have only 10 features, you want to not drop out half of them all the time because you don't see anything, right? If you're blind like this, you cannot see anything. So you have to be like a little, your intuition has to work a little bit with these methods. There's a bunch of knobs, and you can't just say go. But you can do a grid search, say go, come back in 2 hours, and then see what's working and what doesn't, and then you go in that direction, see how that makes sense, and then you continue. So do a grid search, try these things here, read this later. And there's a lot of things you can do with deep learning. This was only the beginning, right? Literally, this was the beginning, and you already beat Nature paper results, so it's not bad. But there's more to be done. Like if you have vision, if you have pictures, if you have video, if you have speech, if you have text in string form, how do you do that well? There's recurrent networks, there's stacked autoencoders, there's GPU implementation, right? There's all kinds of stuff that one can do. So if you have the interest or the desire to participate in this project, we welcome you highly. You can just join H2O's efforts and add your Jira tickets. This is all public stuff. You can contribute to the code, to the source. Pull requests are welcome. And basically by now you know that H2O does distributed in memory big data science and handles it from R, from everywhere else, from the web. And it's ready for you. So thank you very much.
Thank you so much, Arno. And who wants to read the Nature paper and make a big impact on science? We're glad to accept a lot of contributions from the users as well. So please go back one slide. There's a few startups that are beginning to use deep learning H2O as their base project, so they can build bigger things on top. So we'd love to welcome those entrepreneurs to come and join or work with our team closely as you expand this product into what you're building yourselves. As a startup, we are always looking for partners as well as people who are joining us as peers to go make a big splash, big impact in the science world. Today's talk was quite revelation. It took 6 months to write the Nature paper. I'm sure they would love to use the paper, H2O work, to see if they can do better on their own work. I think science is waiting to be changed. So use H2O and go make a big impact and solve some really hard problems. Hopefully that will inspire change in this planet.
So I had a general question, was that this is using effectively just stochastic gradient descent, right? So are there any other gradient or non-gradient based approaches that are amenable to be parallelized easily? Like stochastic gradient is nice because you know everywhere.
Just a quick thing, I asked beforehand. So VLab, which is a joint venture between Stanford and MIT Enterprise Forum on the 16th, is doing an event on deep learning. And Steve Jurgensen, who's doing investing in this space, is our moderator. We have a number of players. We've invited these guys to be among the demo panel. So I brought some leaflets here tonight, so last night for the early bird discount. We always do something on disruptive technology, so I encourage you to take a look and see. You may learn a little bit more if you come to the event. Thank you for your time.